Hello adventurer, welcome to SAS Quest. Today is day 5 of Digital Logic section intake from Zero series, and today we will learn about logic gates. So let's start. So up to now we learned that computer doesn't understand our human language. It only understands being drawn on and being drawn off. And we assign on value to 1 and off value to 0 so that we can communicate with the computer. For example, let's see this. Let's say we have a light and we have on switch and off switch, just like what we have in our home. If you click the on switch or 1, it will turn on the light or give the value 1. If you click off switch, it will turn off the switch or off the light or give the value 0. So it's like this. If you click 1, it will give the result 1 or true. If you click 0, it will give the value 0 or off. A computer doesn't just work with this. Now, up to now, we just learned that 1 will give us 1 and 0 will give us 0. Imagine building a computer with this foundation or this rule. It's pretty much impossible. That's where decisions and condition comes to place. All the computer uses, and this decision and condition is called logic gates. Believe it or not, all the computer you see uses this logic gates, and there are billions and trillions of logic gates in the computer we use, combination of these logic gates. So gate is the very foundation from which computer works. How computer thinks, how computer do tasks, all depends on how logic gate is assembled, how which logic gates is used. So let's start our knowledge or understanding of what logic gates is. As we have said, logic gate is like conditions. As there can be different conditions, meaning different conditions, but some of the very top decisions through which when we use them can make computer are as follows. The logic gates can be divided into three parts. First of all, the basic gates. In the basic gate, you will see OR gate, AND gate, and NOT gate. In another is universal gate. In universal gate, you will see NOR gate and NAND gate. At last, you will see other type of gates. They are YUX OR gate and YUX NOR gate. We'll understand these gates one by one. Let's go with first of all OR gate. OR gate, or as we have said, all these are the conditions. The OR gate condition is that there must be at least one true value or the number 1 for the output to be 1. Otherwise, if there is nothing, no one, it will give an 0 output. That's the uh, that's the conditions of OR gate. Now you might be confused on what this is. We'll understand it bit by bit. The OR gate is represented by this sign. You might have seen it, addition sign. Don't get confused thinking OR gate basically means adding value. It doesn't mean. It means it is just a symbol to represent the OR gate. For example, when I say A plus B or A plus C, A plus C, what this means is not adding them. It means there is A input and there is B input connected by the OR gate. Or this is basically an OR gate. OR gate also has a diagram to represent it. It is represented by the diagram this. Yeah. The diagram there can be, as you can see, this two dot and this. The two dot two line you see is the input, and the on the dot you see here is output. I I want to tell you that There can be multiple inputs. For example, there can be 4 input, 5 input, 6 input in OR gate or any other gate, but there can only be one output. As we have said, this logic gates is like conditions. There can be different conditions, but there can only be one output for these for the conditions. So, so let's understand this better. Let's understand the OR gate better. There is also the thing called truth table, through which we will use it throughout our digital logic, learning. As truth table is the combinations of input, is a combination possible, all the possible combination of input. For example, there is A and B. This the truth table will show us all the possible combinations or all the output combinations possibles. If there is A plus B plus C, B plus C, all the combination can be seen through the truth table. There is limited number of how many output can there be. So truth table varies on the number of input that we give. If there is 2 input, it will give 4 output. If there is 5, 6, 4, 18, the output or the possible combination will increase. Now let's see how we can make the truth table. Truth table is basically input with given output. So for example, as we have said, let's take A and B. Let's make a truth table of OR gate. There is input A and input B. To to solve the to solve or prove that OR gate only gives the value true one, if there is at least one value, we can put pretty much different output, but there can only be one output, as we have said. So let's not do many input. Let's just do two inputs, A and B, and have the output O. Now the input, as we have said, comfortably understand 1 and 0. So the input can well be 1 and 0, and combination of 1 and 0 will give us the output. Let's say the first combination is light being drawn off and drawn on. So 1, let's say there is a switch A and B. This is an figure of OR gate. We understand the OR gate with both truth table and gate. Truth table and the figure. Let's say I give one value to A, or we click the button 1, and we didn't click the button of 0. As the formula said, if there is at least one true value or 1, it will give the output 1. So 1 and 0 will give us the output 1. Let's say I didn't click the A, but rather than clicking A, I clicked B. So 0 and 1. As again, thus, as the condition tells me, the condition is there at least needs to be 1 for the 1 true. Let's say I click the both of them. Now what? Will it nullify them? No, obviously not. It will give us the value 1 as the condition. But let's say I didn't click any of it, 0 and 0. Now the condition isn't fulfilled. The decision cannot be taken. So 0 and 0 will give us the output 0. As we have said, represented or get represented by the plus sign. So the output can be say A plus B, or A or get B. Truth table is this. I hope you understand. The OR gate condition is that there at least needs to be one true value for the output to be true. If there is none, it will only then it will give us 0. Now you may confuse now, but let's move on to our another gate, that is AND gate. This is another type of basic gates. AND gate condition is just opposite of OR gate. It tells me it will only give us the value true if both or all the input value is true. If there is even a one false value, or 0, it will give us the output 0. The AND gate is represented by this sign. You might have again noticed this, it is multiplication sign, but that doesn't mean and it is multiplication as we have said. And the AND gate figure looks like an half circle with an radius. So AND gate looks like this. As we can said, there can be multiple input, but for now let's have two input A and B, which will give us A multiply B, or this multiply can be also represented by dot. So for easier we can say A dot B. Remember, this dot doesn't mean multiplications, it just means just a way to symbolize or represent the AND gate. And the AND gate, let's understand the AND gate conditions with truth tables and the figure. Truth table, increase this truth table. The truth table making processes input, then output A dot B. Let's see with figure 2. Let's say I only clicked A and didn't click B. So 1 and 0, 1 and 0. As we have said, even if there is 1 0, it will give us the value 0. Now let's say I didn't click A but click B. As formula said, it will give us 0. Now let's say I didn't click any of them. As the formula said, if there is even 1 0, it will give us 0. Lastly, let's say I click both of the switch. It will give us 1. So it will only give the true value when both the value is 1. To give you an overview of AND gate and OR gate in like our example, imagine the switch we have did. In previously the switch was like this, where 1 will give, when you click 1 it will give us 1, and when you click 0 it will give us 0. But now with the OR gate, as the OR gate tells us, the OR gate tells me that even if we clicked, if they click one switch it will give us 1. But the AND gate tells me, or the AND gate switch tell me, the light will turn on only if you click the both the switch. I hope you understand. Now let's move on to a very interesting one and a very reverse line or a very important gate, that is NOT gate. This gate is pretty much overlooked, but our all the computer is nothing without this, honestly. So this NOT gate is like a inverter. It turns the input you have given and give the opposite of it. So if we give 1 to this, the inverter, it will give us 0. If you give the 0, it will give us 1. So it is like opposite. If you give a positive value, it will give a negative. If you give a negative, it is a positive. It is represented by this complement sign which we have done in math. It is like to show this guy is like a negative guy. Like imagine this person. So imagine this person as a negative person, or the person that makes things opposite. This it is represented by a single line in the top. So let's say input A inverter or NOT gate is represented by this sign. Let's say A is 1, A complement will give us 0. Let's say A is 0, A complement will give us 1. Diagram of NOT gate is this triangle with the sign, this circle. This is the symbol of NOT gate. Now NOT gate truth table is this: 1 is 0, 0 to 1. There is nothing to really see. And when I say NOT gate is so important, is because NOT gate is used to make the universal gate. So universal gate is called a universal gate. For example, OR, NOR, and NAND are the universal gate because Using this universal gate NOR and NAND, whole computer is made, and NOT gate is used to make this universal. For example, just understand with UNIVAR gate. Let us understand with NOR gate. NOR gate is basically combination of OR gate plus NOT gate. It is, so as we have said, NOT gate makes the opposite of what it is. So it is OR gate opposite is NOT gate. Do you remember the truth table of OR gate? Now let's do it again. A and B with OR gate. So 1 and 0, 0, 1, 1 and 1, sorry, 1 and 1, 0 and 0. 1 and 0 will give us 1, 0 and 1 will give us 1, 1, 0 as the condition of OR gate. Now the NOR gate is basically opposite of OR gate. So 1 will give us the opposite of OR, 0, 0, 1. So the condition of OR gate, NOR gate is that NOR gate will only give us true value when both the input is negative or false. So if you give both 0 and 0, it will give us the result 1. That's NOR gate. It is just opposite of OR gate, where OR gate only gives us 0 when both value is 0. But OR gate only gives 1 when both the input is 0. It is just opposite of OR gate. So from what we understand that UNIVAR gate or UNIVAR gate is a combination of OR gate and NOR gate. It is represented by diagram OR gate, which is this, with the NOT gate in the top. NOT gate is like a circle in the top. So this is the figure of NOR gate, and this is the OR gate symbols, or how we represent the OR gate. We represent the NOR gate. It is basically OR gate with the NOT gate, which is basically the complement in the top. So this is the NOR gate way of representing, and this is the diagram. I hope you understand the NOR gate. Now let's move on to our another favorite, that is NAND. NAND. NAND gate is uh, as just like NOT gate is opposite of what the name is of it is. It is NOT gate plus AND gate. So NOT plus AND is NAND gate. Let's see just like how we did it with OR gate. We'll see the truth table of AND gate again. So truth table AND gate is A and B with AND 1 and 0, 0 and 1, 0 and 0, 1 and 1, 1 and 0, 0, 0, 0, 1. The NAND gate is basically opposite of AND gate, so 0 will give us 1, 1, 1, 0. So from this we can understand that NAND gate gives us true. NAND gate will give us false only when both the input is true. So it is just opposite of AND gate. AND gate gives us AND gate gave us true value only. It gave us true value when only when both the value was true. But NAND gate gives true value all the time, except when both the input is true, it will give us 0 now. This is just opposite of AND gate. So NOR gate it will give us the value true if both the input is 0. And the NAND will give us the value false only when both the input is true. I hope you understand this condition. Now let's move on to our other things, that is possible XOR. Now don't get confused with combination of OR gate. XOR gate tells us that XOR gate tells us that uh, okay, sorry. The XOR gate tells us that it will give us the value true If both the input are different, the input are same, it will give us 0. The XOR gate is just opposite of XOR gate. XOR gate tells us it will only give us the value, it gives us the value true if both the input is same, and if the input is different, it will give us 0. Don't get it confused with being 1 and 0. Let's say, for example, XOR gate. Let's say with a table. XOR truth table. A and B XOR. 1 and 0, 0 and 1, 0, 0, 1, 1. Now, let's see. 1 and 0 is different. So XOR gate will give us 1. 0 and 1 is different. So it will give us 1 and 1 is same. Sorry, 0 and 0 is same. So it will give us value as the XOR gate condition is. It will give the value 0 if both the input is of all the input is same. So 0 and 0 is same. So it will give us 0. 1 and 1 will give us 1, right? No. As their value is same, it will give us 0. What about the XOR gate? The XOR gate will give us the value 0 here, 0 here, 1 and 1 in here. As your XOR gate tells us the condition is that it will only give the value 1 or true if both the input is same. The XOR gate is represented by this plus sign, a plus b, with this a plus b and this circle inside. So it is plus with this circle inside, and the XOR gate is represented by a circle with dot inside. So I hope you understand how to do this logic gates. I tried to dim down and make you understand it as much as I can. So at last, I want to give you a summary of what it is with a light switch. Let's say in the light switch there is, we turn on the light. First, OR gate. The OR gate tells us that there at least needs to be one true value. So, for example, even if you click one switch, the light will turn on. The AND gate. The AND gate tells us we must reach both the switch for the light to turn off. Even if you click one switch button, it will not turn on. That is our AND gate. Now the NAND gate, as NAND gate has only one input. NOT gate. NOT gate only has one input, so one switch. If you click the on switch, it will not turn on, so 0. If you click off switch, then it will turn on. That is NOT gate. Sorry. Now let's go to our universal gate. First of all, NAND gate. NAND gate tells us that in a switch, it will only turn off when both the switches click on. So it will glow the light even if you didn't click anything, or if you need to click one switch. It will only turn off the switch if you click both the switch. That is an AND gate. But in NOR gate, it will only turn on if we didn't click anything. If you click the light button, just for example, if we click both light button, it will turn off. If you click even one, it will turn off. If you click nothing, only then the light will turn on. That is NOR gate. Now let's go to XOR gate. In XOR gate, the light, as we have said, if both the input is same, for example, let's say I click both the switch, the light will turn off. If I didn't click anything, for example, if I didn't click anything, so for example 0 and 0, the light will turn off. But let's say I click even one of them, the light will turn on. If I click this A, it will turn on. If I click not the A but another one, it will turn on. So there at least there needs to be different input. Now XOR tells us there at least needs to be one And there needs to be same input. So for example, if I didn't click anything, so 0 and 0, it will turn on. If I click even one switch, it will still turn off because I just there it was there the input was different. But if I click both of the switch, it will turn on. I hope you understand with this example. I try to teach or simple down this as much as I can. So I hope to meet you in next video. Bye bye. Bye bye.